All right, let's do this. Today we're going to turn back the clock, way back, to the very dawn of the personal computer. This was a time when programming meant you were talking directly to the silicon heart of the machine. We are going deep inside the legendary Intel 8080 microprocessor.
You know, this one quote from a really famous programming book of the era, it just perfectly captures what it was like to be a programmer in the 1970s. This wasn't about elegant interfaces or high-level languages. Oh no.
It was all about painstaking, meticulous, manual effort. And that right there, that was the job. Every single operation had to be crafted by hand, bit by painful bit. So that brings us to the big question for today, right? How in the world did these pioneers take the most basic language you can imagine, just ones and zeros, and use it to build the foundations for all the software that came after? Okay, so let's get into it. The fundamental problem, really, was communication. You've got this incredible new brain, the microprocessor, but it has a language that is, well, incredibly limited. The entire vocabulary of this processor is called its instruction set. And at the end of the day, every single command, add this, move that, jump over there, it's all just a specific pattern of ones and zeros. That is literally the only thing the chip understands.
I mean, can you imagine flipping switches for hours just to enter a single program? One wrong flip and boom, you got to start all over. It was so tedious and just begging for mistakes. So pretty quickly, programmers adopted hexadecimal, that's a base 60 number system, as a kind of shorthand. But honestly, it was still just a slightly more convenient way of writing raw machine code.
So, this grueling reality, it led to the first major leap up what we call the ladder of abstraction. If the problem was translation, what programmers really needed was, well, a translator. And that is exactly what an assembler is. An assembler is just a clever piece of software that does all that boring, repetitive work for you. The programmer gets to write in a source language using simple, memorable commands, and the assembler translates it into the object program. You know, the raw numbers the microprocessor can actually understand and execute. In this slide, I think this just visualizes that translation perfectly. Look at the left side. You've got the human-friendly stuff, move AM. That's easy to remember. It means move the data from a memory location into register A. But on the right, you see what the computer actually sees, 70E. The assembler's whole job is turning that simple phrase into that number.
But here's the thing. The assembler didn't solve everything, not by a long shot. It made writing the code easier, for sure, but it didn't help with the bigger problem, which was this massive gap between the simple things a processor can do, like adding two numbers, and the really complex things a user wants it to do, like run a game or control a piece of industrial machinery.
So how did they bridge that gap? Well, a programmer had to get to know the inside of that chip intimately. They had to absolutely master its core vocabulary, its toolkit. And this was pretty much their entire workspace. You've got the work registers. Think of them like tiny little scratch pads for holding numbers. Then there's the program counter, which is a pointer that's always telling the chip, okay, execute this instruction next. And the condition flags. These were absolutely crucial. They were just single bits that would flip on or off to record what happened after an operation, like, did that last calculation equal 0? So check this out. When a programmer wrote add M, they weren't just thinking add. They were picturing a very specific operation inside the chip. Okay, take the byte from the memory location my H and L registers are pointing to and add it to the byte that's currently sitting in my main scratch pad, the accumulator. It's incredibly direct and incredibly granular. And this right here shows that a single one-byte instruction does so much more than just math. I mean, look at all those flags it messes with. After add M runs, the carry, the zero, the sign, the parity flags, they're all updated based on the result. And a programmer could then use those flags to make decisions, to completely change the entire flow of the program. So how do you get from a simple add command to a program that actually does something useful? Well, you start combining these simple little building blocks into larger, more powerful structures. And the most fundamental of all of these is the loop. Okay, so this is what a loop actually looked like in 8080 assembly code. The instruction DCRB, that just means decrement register B. It's our loop counter, our countdown timer. The next instruction, JNZ beacon, now that is the crucial part. It means jump, if not 0, to the label beacon. So as long as our counter in register B hasn't hit 0, the program just keeps jumping back to do the code again. And you know what? This simple logic is the heart of pretty much every computer program ever written. You set things up, you do the work, you check if you're done, and if you're not, you go back and do it again.
The code we just saw is a perfect low-level example of this universal idea.
All of this really highlights something important. Programming the 8080 wasn't just a science. It was an art, a craft. It required a very specific mindset and an intense, almost obsessive attention to detail, because that machine would do exactly what you told it to, even if what you told it was a huge mistake.
And oh man, the mistakes were so easy to make. Forgetting to load a starting value into your loop counter, or using jump on carry when you really meant jump on not carry, a classic logic bug. Or just not realizing that a certain math operation would unexpectedly flip the zero flag and completely mess up the next part of your code. Every programmer had to become a detective.
So here's the crucial point. Writing the code was only half the battle. This quote just nails it. The often neglected, totally underappreciated part of the job was debugging, hunting down those inevitable errors, sometimes for days, just to figure out why the program wasn't doing what you thought it should be doing.
You know, the entire history of early software can really be seen as this climb up a ladder of abstraction. Each rung on that ladder going from binary to hexadecimal, then from hex to assemblers, from simple instructions to reusable macros. It was all about getting further and further away from the tedious mechanics of the hardware and closer to actually solving the problem at hand.
And wow, have we climbed high since then. The 8080 executed one instruction right after the other, in a straight line. A modern processor is a whole different beast. It uses wild techniques like instruction-level parallelism to figure out on the fly how to execute tons of instructions all at the same time.
But that brings us to our final thought. Each rung we climb on that ladder, it gives us more power, it makes our jobs easier, but what do we give up in exchange? What vital, low-level connection and control over the machine do we lose when we no longer have to speak its native tongue? It's definitely something worth thinking about.